Hi, everyone. Having defined the Lebesgue measure and Lebesgue measurable sets in the previous video, we now want to observe some properties of Lebesgue measure. In doing this, we will actually return to that original wish list we had for what the properties we would like a type of measure to have, to see that we are actually able to recover some of those properties with the Lebesgue measure. So to begin, we first want to look at additivity. Now recall that for the Lebesgue outer measure, we were able to prove that the Lebesgue outer measure satisfied a type of countable subadditivity. What we want to show here, however, is that the Lebesgue measure is indeed additive. So let En be a countable sequence of pairwise disjoint measurable sets. Okay, recall that when we say pairwise disjoint, right? What we mean here is that EJ intersect EK is the empty set for all J and K not equal to each other, right? So if you take any two of the sets, then their intersection is empty as long as you're actually not writing the same set here. So let En be a countable sequence of pairwise disjoint measurable sets. Then we get that the Lebesgue measure of the union of the ENs is equal to the sum of the measures of each EN. So the way you can sort of think about this theorem, what it's saying is you have these sets, say E1, E2, right? And these are really subsets of R, but I'm sort of drawing them in R2. But you have these disjoint sets, and you have a countable sequence of them. What they're saying is that you could either take the measure of E1, the measure of E2, the measure of E3, so on and so on. You could take all of those measures and add them up, right? That would actually give you the same thing as considering the set, which is just the union of all of the ENs and taking its measure. Okay, you ought to get the same thing. Now, of course, this pairwise disjoint condition, you can sort of see why that's necessary, right? In general, if I had two sets that look like this, E1 and E2, if I took the measure of E1 and the measure of E2, I would be double counting the intersection of E1 and E2. So that's the reason for this pairwise disjoint condition. We didn't need that for subadditivity because that actually works in the direction of the subadditivity, right? So it's okay for subadditivity. You don't need to require them to be disjoint, because if they're not disjoint, then you're just going to overcount a little bit more in this sum. All right. So what we want to prove is that for Lebesgue measure, this countable additivity holds. Now, again, let me sort of emphasize here, when we talk about Lebesgue measure, in some ways it's no different than outer measure, right? The Lebesgue measure of a measurable set is the same as the Lebesgue outer measure of that measurable set. But what we're really doing is we're restricting the types of sets we talk about being measurable, right? So that Carathéodory condition, that is a condition that not all subsets of R satisfy. We haven't proven that yet, but it's a special condition. And so what we're really doing is we're saying that another way of thinking about this is that the Lebesgue outer measure is countably additive as long as you restrict the types of sets you're measuring, right? All right. So let's walk through a proof of this. So we're going to actually do this first by proving it for a finite number of sets. And eventually we want to prove this for some countable collection. But let's start first with sort of case one. And let's assume that the collection of sets En is a finite collection of sets. Okay. So we can sort of imagine here that there are K of these sets. All right. So the way we're going to prove this actually is by induction. Okay. So we want to prove that the measure of, again, here we have a finite union. So we want to prove that this holds. And we want to do this for, like, no matter what size, no matter how many things we have in our union. So K is sort of the number of things, the number of ENs we have. We want this to work for any finite value K. So anytime you're trying to prove a statement holds for all natural numbers K, induction is often a good method of proof. So to execute a proof by induction, we need a base case. Okay. And in this case, we'll just take K is equal to 1. So we want to prove that this holds when K is equal to 1. Well, when K is equal to 1, I mean, what is the claim here? The claim here then is mu of the union n equals 1 up to 1 of En. Well, what is that? I mean, a union, but it's just one thing. So it's just E1. Okay. Well, that's the same thing as adding up from n equals 1 to 1, all the mu of ENs, because again, that would just be mu of E1. So this is true in the base case. And as is sometimes or often the case with the base case, it's almost trivial, right? All right. Now we need the sort of inductive step. It's been a little while since we've done anything by induction. So let's just remember. So what we're going to do is we are going to assume that this holds for K elements and show that that implies that it holds for K plus 1 elements. Okay, so assume that mu union n equals 1 up to, sorry, I'm going to assume that it holds for K minus 1 things and prove that it holds for K things. You can do it either way, but to be consistent with my notes here, let me do assume it's true for K minus 1 things. Okay. And now I want to show that this implies that the statement has to also hold for K things. Okay. So I'm going to assume that it holds for K minus 1 things. I'm actually not going to use that immediately. Let me start by making a couple of observations that at first are going to seem maybe a little strange, like, okay, this is true, but why do we care about this? So note that since the En are disjoint, okay, I want to make a couple of sort of set theoretic claims. Okay, so the first thing I want to note is that if I take the union n equals 1 up to K of En, and I intersect that with Ek. Well, let's think about this. What am I going to get? So I have a union of all these things, but they're all disjoint, and I intersect that with Ek, but Ek is one of the things in this union. The only thing I'm going to get back is Ek. And the other thing I want to note is that the union n equals 1 up to K intersect, oh, sorry, of the ENs, intersected with Ek complement. Well, what would that be? So this is the collection of all the ENs union together from 1 up to K, and you want to intersect it with all the ones that aren't in EK. Well, that's just all the other ones other than EK. So this gives you the union n equals 1 up to k minus 1 of En. All right. Now, you might be looking at that and going, okay, great, that's true, but why should I care about that? Well, let's see what we can do here. Leave these orange claims down here so we can use them here momentarily. Now notice that, right? The set EK, right? Doesn't matter what K is for any K. Note that EK is measurable. And so we can apply that Carathéodory condition to say for any subset A of R, mu star of A ought to be equal to mu star of A intersect EK plus mu star of A intersect EK complement, right? That's what it means for the set EK to be measurable, that this condition is satisfied. Well, now you may start to see, if you look here and you look here, okay, this condition holds for any set A. So what if I look at it in the particular case that A is equal to the union from n equals 1 up to K of En? So then that gives me that mu star of the union n equals 1 up to K of En is equal to mu star of union n equals 1 up to K of En intersect EK plus mu star of union n equals 1 up to K of En. Let me be a little careful here to put some parentheses in here to disambiguate this. Intersect EK complement. So all I'm doing is taking this and I'm substituting in, this holds for every subset of R, I'm substituting in A is equal to union n equals 1 to K of En. Okay. But now notice, right, we now know simpler ways of expressing these things, right? So I have mu star of union n equals 1 up to K of En, which is equal to, this is just mu star of EK plus mu star of the union n equals 1 up to K minus 1 of En. All right, now I can get rid of these set theory calculations I had done. Now, notice that the EK is measurable, and each of the ENs is measurable, so each of these unions is also measurable. So the outer measure is actually equal to the Lebesgue measure because these are measurable sets. They're either measurable sets or unions of sets that we know are measurable. Okay, so since unions of measurable sets are measurable, then we get that the measure of union n equals 1 up to k of En is equal to the measure of Ek plus the measure of the union n equals 1 up to k minus 1 of En. All right. But now we can actually use our inductive hypothesis, right? At the beginning, we assumed that the measure of the union n equals 1 up to k minus 1 of En was equal to, so we're going to keep this first term, but we assumed that this term was equal to the sum n equals 1 up to k minus 1 of the measures of En. Okay. Well, now notice we just have here, what do we have? We have the measure of E1 plus the measure of E2 plus the measure of E3, all the way up to the measure of E sub k minus 1. And then we've got a plus the measure of Ek. This is just the sum, this whole quantity, I can just lump this into the sum, becomes the sum n equals 1 up to k of the measure of En. Okay. And so we notice that this is indeed exactly what we wanted to prove, right? We have proven that the measure of the union n equals 1 up to k of the Ens is equal to the sum n equals 1 up to k of the measure of each En. Okay. So at this point, we can pause. Let's think about what we've done. So for a finite value k, by induction, we have proven that for every natural number k, the measure of the union n equals 1 up to k of En is equal to the sum n equals 1 up to k of the measures of each of the Ens. Okay. But that's for, basically we've proven this for all finite unions now. Okay. Now, however, we need to prove this for countable unions. Okay. So we've done it for finite. Now we need to do it for countable. And we'll see actually that having done it for finite and for every finite union actually helps us out quite a bit now in proving that this also works for countable unions. All right, so we're done with case one, right? Which is the set is finite, the set of Ens is finite. Okay. And now we're going to move on to case two, where we look at what happens when the collection of sets is countable. All right. So on to case two. So this is countable. All right. Well, notice that I want to think about this union now, n equals 1 up to infinity of En. But notice that this contains any finite union, right? So if I stop after some k in taking the union, that'll always give me a subset of the full sort of countable union. Okay. Well, then by monotonicity, what happens? Well, by monotonicity, mu of the union n equals 1 up to infinity of En must be greater than or equal to mu of this finite union. Okay. And so that's just monotonicity. But now we've proven that for finite unions, we get countable we get additivity. So this is just the sum n equals 1 to k of mu of En. All right. So if I look at this thing on the right-hand side here, what do I have? Well, as K increases, this is non-decreasing, right? And in fact, right, it's gonna, these values could be zero, right? You could, one of your ENs could be, have measure zero, but that you can never have negative measure, right? So each term here is greater than or equal to zero, which is why this is non-decreasing in K. It's also bounded above by whatever the measure of this set happens to be, right? So I don't know what the measure of this set is, but I know that it's a countable union of measurable sets, so it is measurable. So this has some value. This is non-decreasing and it is bounded above. Since it's non-decreasing and bounded above, then by the monotone convergence theorem, right? If I take I can take a limit of both sides as k goes to infinity. This doesn't depend on k. Okay. This, as k goes to infinity, must converge by the monotone convergence theorem. And we will call, right, we just write this, the limit as k goes to infinity is the sum n equals 1 to infinity of mu, sorry, this is still an inequality, en. All right. So I get this, which again is not quite what I want, right? But I have an inequality here by countable subadditivity. Right, remember, I already have countable subadditivity. I get the other direction. So by countable subadditivity, the measure of the union n equals 1 up to infinity of en is less than or equal to the sum of the measures. Okay. And so now, combining these two, I get the result that I want. So hence, the measure of the union n equals 1 to infinity of the ens is the sum n equals 1 to infinity of the measures of the ens. Now, just a small point here, when we apply countable subadditivity, you could say, wait, we proved countable subadditivity for outer measure. But again, remember, these are both measurable sets. So the measure is just the outer measure, right? So you can write down countable subadditivity for the outer measure, but then its measure is just equal to the outer measure. And so you get countable subadditivity for the measurable sets here. All right. And that concludes our proof, right? So one nice thing that we're seeing here, right, is that if we restrict ourselves to measurable sets, to Lebesgue measurable sets, we don't just get countable subadditivity anymore, we actually get countable additivity, which is really nice. I mean, this really says that this is working in precisely the way we sort of think that a measure should, right? If I take two disjoint sets, or indeed countably infinitely many disjoint sets, as long as they're all measurable, then I can find the measure of their union by just finding the measure of each individual set and just adding them all together. Now, in the next video, I mentioned or I think I mentioned in a previous video that we will eventually look at non-measurable sets. And indeed, one of the things we'll see is that we're able to show that some things are non-measurable by showing that you actually don't get this sort of nice additivity. So we'll see that there are just some things that break down when we start dealing with non-measurable sets. All right. The other property that I want to look at in this video of Lebesgue measure is we could sort of think of it as continuity. Another way to think about it is just like this is sort of, it's an analog to unions, so but it's for intersections, okay? And I'll explain, once we talk through the theorem, I'll sort of explain why it's sort of like continuity. So let En be an infinite sequence of nested measurable sets. So we're really saying by nested, right, that E sub n plus 1 is a subset of En for each natural number n. If the measure of E1 is finite, then the measure of the intersection of all the EKs, so k equals 1 up to infinity, the intersection k equals 1 up to infinity of EK, the measure of that set is equal to the limit as n goes to infinity of the measure of each En. Okay. So if we sort of think about what's going on here, so we have these nested sets. So you start with a set E1, and then somewhere inside it you have a set E2, and a set E3, and so on and so on and so on. And what's happening in a way is this this intersection, right, is sort of giving you their limit. It's telling you, you know, what is sort of contained inside of all of these EKs, right? So one way to think about this is sort of like, it's sort of like the limit of the EKs. And so then what this is saying is, if you think of this as a limit, then you can pull the limit outside of the measure. Okay, so that's in some ways why this is called a sort of a continuity of Lebesgue measure, in exactly the same way that we might have shown the limit as x approaches a of f of g of x, right, under the appropriate conditions, right? This is the limit as, or sorry, this is f of the limit as x approaches a of g of x, right? And that condition was that f ought to be continuous, right? I can push a limit inside a function, in this case, as long as f is continuous at g of a. Okay. All right. So we want to prove this theorem, okay? And then the last thing I want to do in this video after we prove this theorem is sort of see how this can be applied to actually help us find the measures of some other sets, right? We've found the measure of a few things, right? But it'd be nice to look at sort of maybe a non-interval type of example. All right, so let's take a look then at the proof of this theorem. All right, so I'm going to just give a name to this intersection. So this k equals 1 up to infinity of ek. I'm just going to call that E, right? So if we come back over here, and maybe again, this will be sort of helpful as we go along. Let's sort of redraw this picture. I'm only going to draw a couple of levels. Okay, and then imagine again we're settling down to some set inside here, E. So imagine this E in blue is in the intersection of all of the EKs. All right. So I'm just giving a name to that intersection. All right. And now I want to define a sequence of sets, which I'm going to call the FKs. They are going to be EK minus EK plus 1. Okay, so what are these sets? Well, F1 would be E1 minus E2. It's just the in-between stuff here, right? So this would be F1. F2, right, you could think of as being the stuff in here, right? So it's just the sort of the in-between stuff. And the nice reason for doing this is if you define it in this way, then the FK are pairwise disjoint. And now you go, ah, right, I have a theorem about things that are pairwise disjoint. Maybe that's going to come into play. And indeed it will. Okay. And further, not only are they pairwise disjoint, if I take their union, I'm also getting a union of pairwise disjoint things, right? It's leading you to where we're going. So what would the union of all of these FKs be? Well, you would get everything, but you wouldn't get E. You wouldn't get the stuff sitting inside E. So you'd get everything inside of E1 except for E. So you'd get E1 delete E, right? Okay. Now, let me point out this minus here, right? And it'll be helpful later on. If we write A minus B, we should think of this as A intersect B complement, right? So you can think of this E1 minus E as E1 intersect E complement, right? Now, the minus is helpful for often just thinking about what's actually going on. But this is going to give me an E1 intersect E complement that sort of pops up in that Carathéodory condition sometimes, right? So again, we just sort of keep those things in the back of our mind. All right. All right. So since E1 and E are measurable. Now, how do I know that? Well, E1 is assumed to be measurable. E is an intersection of measurable sets, okay? And countable intersections are indeed countable intersections of measurable sets are measurable. So E is also measurable. So E1 and E are both measurable. Then E1 minus E, which again, this is just E1 intersect E complement. This is also measurable. Why? Well, E1 is measurable, E is measurable, so E complement is measurable. And the intersection of measurable sets is measurable. All right. Then, okay, I look at the measure of E1 minus E. Well, E1 minus E, that's really, right, we said earlier, this is the union K equals 1 up to infinity of these FKs. But remember, these FKs were pairwise disjoint, and they're also each measurable. Okay. So this is equal to the sum K equals 1 to infinity of the measure of Fk. All right. So we've used the countable additivity of the FKs here. Okay. Now, by our definition of Fk, right? Fk was Ek minus Ek plus 1. So this is really the sum K equals 1 to infinity of mu of Ek minus Ek plus 1. All right, so so far what I have is I have that the measure of E1 minus E is equal to the sum K equals 1 up to infinity of the measure of Ek minus Ek plus 1. All right. Now I need to figure out some ways to express something else. We're going to come back to this, but we're going to sort of sidestep this issue just momentarily. Okay, so let's look at the Carathéodory condition applied to some particular sets. Okay, so since E is measurable, And I'm getting tired of writing measurable, so I'm going to write M bull here. We're going to write this several times more. So since E is measurable, by the Carathéodory condition, that means that mu star of A is equal to mu star of A intersect E plus mu star of A intersect E complement for any subset A of R. Okay. So if I let A be the set E1, then what do I get? Then I get mu star of E1 is equal to mu star of, of E1 intersect E plus mu star of E1 intersect E complement. So now if I look at these, okay, E1 is measurable. So this is just mu of E1. E1 intersect E is just E, right? E1 intersect E. E is a subset of E1, so E1 intersect E is just E. So this is just mu star of E, but E is measurable, so this is just mu of E plus, now E1 intersect E complement, oh, sorry, that should be complement up here. That's really just E1 minus E. We've already talked about it's measurable, okay? So this is just mu of E1 minus E. Now, notice that this implies that, I'm just going to rearrange this. So this implies that mu of E1 minus E is equal to mu of E1 minus mu of E. Notice that from this piece up here, we've gotten this. Okay, we'll be able to replace this with that. Okay, now, by a similar argument to what we did here, so similarly, I can write that the measure of EK minus the measure of, the measure of EK minus EK plus 1 is equal to the measure of EK minus the measure of EK plus 1. Okay. Now, how do I do this? Well, I basically use the fact that EK plus, I use the fact that EK plus 1 is measurable. So the fact that since EK plus 1 is measurable, I get like this with EKs here. And then I substitute in, instead of substituting in E1, I substitute in EK plus 1. Okay. And that ends up, maybe I said that the other way around. Let me, you use the fact that EK plus 1 is measurable. So you write down this with EK plus 1. And then you substitute in for your A, you substitute in EK. So then you get the measure of EK is equal to the measure of, this would be EK intersect EK plus 1, which is just EK intersect EK plus 1 is just EK plus 1. This would be the measure of EK plus 1, plus you get the measure of EK minus EK plus 1. So you get both of these things. Now, we're going to combine these up here. Okay. So let me do this in such a way that I save some of my work here. I do want to save, at least for the time being. All right. All right, so now it sort of becomes follow the bouncing ball from here. All right, so I'm going to start with this. All right. So I've got from here, sorry, I've got mu of E1 minus mu of E is equal to mu of E1 minus E. All right. And now from here, I've got mu of E1 minus E is equal to this sum. Is equal to the sum. Let me not get up into the, is equal to the sum k equals 1 to infinity of mu of ek minus ek plus 1. All right. But now, from, well, where is it? Right here. Okay. I can rewrite this. This is equal to the sum k equals 1 to infinity. Mu of ek minus ek plus 1 is mu of ek minus mu of ek plus 1. Okay. And now we can give ourselves some more room because then we've used all of our pieces here. That's a little bit more room. And if I look at this infinite sum I have here, I can express this as a limit, right? This is the limit as n goes to infinity of the sum k equals 1 to n. So now this is a finite sum of mu ek minus mu of ek plus 1. Okay. But now this is a telescoping sum. So if I think about writing out what happens here, so let me keep the limit here. Now this is a finite sum. So what am I going to get? Like if I start with k is equal to 1, I'll get mu of E1 minus mu of E2. And then when k is 2, I'll get a plus mu of E2 minus mu of E3. So what happens is I'll get a mu of E1, and then I'll get cancellation all the way up until the nth term. I'll have a minus mu of En plus 1, which will not cancel out. And so I have the limit of this thing. Well, if I look at this, this is a constant term. Sorry, that's mu of E1. Yeah. Minus, I'm left with the limit as n goes to infinity of mu of E sub n plus 1. And now, since mu of E1 is finite, I can cancel this from both sides. And what I'm left with is that the measure of E must be equal to the limit as n goes to infinity of mu of, we have En plus 1 here, but we could just as well say En, right, as the index here goes off to infinity, right? And this is precisely the result that I wanted to establish. Okay. So we get these nice properties both for, we get the additivity, which again really is saying something about unions of disjoint sets, of disjoint measurable sets, pairwise disjoint measurable sets. And we also get this sort of continuity result for nested sequences of measurable sets. Okay. So again, both of these are really nice. They're going to come in really handy when we start doing Lebesgue integration. And so we'll see that these are really nice properties to have of the measure. Now, as I mentioned, I want to just briefly finish out this video by looking at one more example of a measurable set, and in particular one for which we can make use of actually this continuity property that we've just established. All right. So some of you may have seen before this set called the Cantor set. Now, let me briefly describe what the Cantor set is and how we can define it. So the idea is I start with the interval 0, 1. So I've got labels down here for sort of the lengths. We're going to define this in sort of an iterative way. So we start with the set C0, and we take C0, we remove the middle third, right? So we remove the open interval from 1/3 to 2/3. And that gives me C1, okay? So I take C1, right? Or, sorry, I take C0, remove the middle third, that gives me C1. Now, I take C1, which is now really just a union of two closed intervals. I remove the middle third of each of those, and that gives me C2. Now, C2 is just a union of four closed intervals. From each of those disjoint closed intervals, I remove the middle third, and I'm left with 8 disjoint closed intervals. I remove from each of them the middle third, right? So I iteratively do this. The Cantor set, which we call C, is in fact the intersection k equals 0 to infinity of all of these CKs. Now, you can ask all sorts of questions about this set. Now, one which we will not prove, right, is that in fact C is uncountable. Okay, so there aren't countably many things in the Cantor set. There are uncountably many things. This is a little tricky to prove. I mean, it's not very tricky. The idea, though, is that you show that essentially everything in the Cantor set can be represented in like a base 3 expansion in a particular way. So its base 3 decimal expansion has only zeros and twos as digits. And so then from that, you argue that there can't be countably many things, essentially. So C is uncountable, just bigger than the rationals in terms of cardinality, right? But we can also ask what its measure is. Now, this is where you may stop for a second. We've proven, for example, that every countable set has measure 0, or rather, we showed that the rationals have measure 0. We showed they have outer measure 0. And I said, well, you could adapt this proof for any countable set. And once you have that every countable set has outer measure 0, we prove that every set that has outer measure 0 is Lebesgue measurable. So therefore, its Lebesgue measure must be 0. So every countable set has Lebesgue measure 0. So every countable set has Lebesgue measure 0. And you might wonder, well, what about uncountable sets? Can an uncountable set have Lebesgue measure 0? Well, let's actually take a look at these. Now, when you look at this, the first thing you might say is, well, I have each of these CKs, and I have a countable intersection. Can I use my continuity theorem? Well, let's ask ourselves, are the CKs nested? Well, sure. C2 is a subset of C3. Or sorry, C2 is a subset of C1. C3 is a subset of C2. Because we define this by removing middle thirds, right? It is necessary that the CKs are nested. Okay, so we can check that the CKs are nested. Okay. Each of the CKs are measurable. Why is that? Well, each fixed CK is a finite union of intervals. Intervals are measurable, and the union of measurable sets is measurable. So each of these is measurable. And finally, C0 has finite measure. Right? In fact, C0 is an interval. It has measure 1. So from our previous theorem, we can conclude that the measure of C, which is the measure of the intersection of these CKs, where K equals 0 up to infinity, this is the same as the limit as n goes to infinity of the measure of the CNs. Okay. But now you have to ask yourself, well, how can I express the measure of Cn in terms of n? Well, if I look at each of these, okay, so I ask myself, what's the measure of Cn? Well, notice that here I have one interval, here I have a union of two intervals, 4 intervals, 8 intervals, 16. So one of the first things you can observe is that each of these, at each level, right, at the kth level, you have 2 to the k intervals, okay? And what is what's the length of each of those intervals? Well, the first one has length 1, then each of these has length 1/3, each of these has length 1/9. So in the kth step, you have 2 to the k intervals, and each of those intervals has length 1/3 to the k. Okay, so your total, you have, or n, 2 to the n of these, each one of them has length 1/3 to the n. So you actually get, right, that the measure of Cn is 2/3 to the n. So down here, then, the measure of C ought to be the limit as n goes to infinity of 2/3 to the n, which is 0. So the Cantor set, while being uncountable, still has measure 0. Okay, so there's not some nice correlation between countable and uncountable and whether Lebesgue measure is 0 or non-zero, right? It doesn't quite work out that way. Okay. So this is just a nice example of how you can use some of these properties to prove things about the measures of some more exotic sets, right? This is much more interesting than just a single interval or some measure 0 set. All right. Now, I want to conclude this video by just revisiting, we talked about this earlier, but I want to sort of revisit our wish list. And I just want to emphasize what we've done in the way that we have defined Lebesgue measure. So remember, our goal at the very beginning was to come up with a function that assigns a size to subsets of R with the following properties. We wanted the length of each interval, we wanted the measure of each interval to be its length. Done, right? We have made sure that happens. We've shown that all intervals are measurable, and we have also shown that the outer measure of an interval is its length. Therefore, the measure of that interval is its length. All right. Translation invariance. We showed that the outer measure is translation invariant. Therefore, the measure is also translation invariant. Okay? Because for any measurable set, right, its measure is equal to its outer measure. Okay. Now, it's these last two where we've played around a bit. When we were only considering Lebesgue outer measure, we weren't able to get countable additivity, right? In fact, we sort of reduced this and said, well, what about countable subadditivity? However, for outer measure, we were able to get that every subset of R was outer measurable. But ultimately, the choice we've made in defining a measure, in defining the Lebesgue measure rather, is to prioritize this countable additivity. So Lebesgue measure is countably additive. However, not every subset of R will be measurable. Now, that is a fact that we still have not established, but will be the subject of the next video, in which we will discuss the construction of the so-called Vitali set, which shows that there are subsets of R which cannot be measured.